initially we created a time series data, and our intention being making the machine to learn to detect the change in this amplitude as well as the frequency, right? We are expecting the machine to learn this. So the type of network we are going to design here uh, to train and test is the Adaline time series networks. Okay, they are capable of identifying this change, right? So this is a prediction network, and it has to predict the change. So we want to check that how quickly the machine is going to adapt to the change in the input. So we make sure that there is a change like this to the network, and machine has to change according as per whenever the input changes, output also is expected to change. All right, so 2.5 sine omega t, omega being 4.1 pi. And the second half of the signal, we have changed the amplitude from, you can see here, initial amplitude is 2.5. We changed that to 0.4. That's the first thing. And we also change the frequency, right? Sine omega t. So omega is 4.1 pi. Lower frequency becomes a higher frequency, some 18.66 pi. All right, so t1 and t2, right, 0 to 3 seconds, first 3 seconds we send the first signal, and the second half, 3 seconds till 6 seconds, we are going to generate like this. Okay, so let's see, let's run this and see. Okay, so anyway, that part is done. So we created the signal, right? If you want, you can definitely plot, right? I'll just plot it and show it over here. So I'll run in the command window. Okay, so this is what's going to happen when you run this. Okay, so when we run, we are able to see this, right, as a output. You can see that initially you have a higher amplitude, lower frequency. So 2.5 is the maximum peak and the minimum peak. At the same time, you can see after 3 seconds, which is here, right, after 3 seconds we can see that this changes. Okay, so amplitude reduces to a smaller value. We can bring our cursor and we can see the value. Okay, so even the minimum value is going to change in a very similar fashion. So we have this changes, and the time is after 3 seconds till 6 seconds is the change. Right, now this is what is the time series we are creating. We expect the machine that we are going to generate now, machine also to learn the same way. All right, so we'll move on to the next part. So in this code, right, so this is the code required. So we initially declare the parameters and define the network. All right, so with the same this thing, we'll try to plot both the original sequence and the predicted sequence, so that we can, right, understand that whether the machine is capable of adapting to the changes in the input. Okay, right, for that, we, if you remember, we need to convert that sequence, right, contour sequence, that's a continuous signal, into a sequence. We convert that, right? So we define the parameters such as the delay 1 to 5, 0.2 second, sorry, learning rate we kept as 0.2. Definitely you can make the changes here. Then convert the, you create a layer, it's called as a linear layer, with the input delay and the learning rate. Create a network, which is the required Adaline network. Okay, so Adaline network can be defined by using adapt, pass the network you created, and this P is the input, P itself is your output. You want the machine to understand the change in P. So what is P? P is the sequence that we created from Y. The Y has been defined as a continuous signal which got converted into a sequence over here. So that P sequence you provide as input to the network, and network is expected to uh, learn or adapt to the changes in Y or in P, basically. right? So after the training happens, you get the results in y, you get the results in the net, which is the uh, identifier for the neural network, and y is the output that the machine produced during this learning process with the error signal. So now we try to plot y and e here. Okay, so if you want to plot this, you need to convert that into what you call as the right continuous waveform, right? So for which you can use sequence to con, right? So that creates, so both the y output and e will be converted, okay, into the continuously plottable format so that you can plot them, right? So the figure will be used to plot them. So we use two subplots. The first subplot is for what you call as the y and the y. So we have both the y's. You can see here initially we created a small y. So that small y will be in B. So that is a blue color, and the machine's output will be in the red color, right? Okay. Then we also plot the error signal. Okay, let's just run this section to see the outputs. So it's actually running now. It created the required amount of error as well as this thing. Okay, let me just bring the error waveform here. Right, you can see that the original signal and the predicted signals do match. They are overlapping on one another. So that means initially there is no error. As soon as there is a change at 3 seconds, you have an error. All right, so that means you can get the exact values like this. So machine learns here. I think the uh, let me reduce this amplitude so that it becomes very clear. Okay, let me save this. Let me run once again so that we can see the complete graphs. Okay, I'll run this once. Okay, it looks pretty clear now because the fact that now we reduce the amplitude as well as the frequency. Okay, so initially you can see that machine takes some time to learn, right? You can see here the red line, the red dashes are what machine is producing, right? You can see that there is a small amount of difference among them, right? They're not coinciding initially, but after say 1 second or something, you can see that there is no difference between them. They completely coincide, indicating that yes, machine has learned. So the other view of that is through the errors. You can see here, this is the amount of error which is present, the second graph. So there is error, but after some time you can see that error reduces. Error is very less, right? Very close to zero. But at t equal to 3 seconds, you can see that we all of a sudden changed our input sequence, right? So we change the amplitude, we reduce the amplitude, we increase the frequency. So machine is yet to predict that, right? All of a sudden at that moment where the input changes, there is a lot of error because you see that, right? Machine is expected to go up, machine's output is expected to go up, but all of a sudden you change your input to come down, right? So because of that, you have a huge amount of error, right? Yes. But instantaneously machine learns, right? It adapts to the change in the input, and you can see that all of a sudden the error can become zero within maybe 0.5 seconds or less than that, right? Once again, initially you can see there is a difference between the input and output values, but instantaneously after 0.5 seconds or something max like that, within that duration machine learns, and again you can see that error becoming equal to zero after that, right? Error is negligible initially, closer to 4 seconds, but after that you can definitely see that it has reduced. Yes. Right, so this is the machine learning algorithm called Adaline, which is a part of a neural network. Okay, so that was our code, customly written built neural network, code number 4. And also in the same class, we did another code for the multi-layer perceptron based XOR gate. So fundamental XOR gate we had created at the very beginning of this course, but now we are trying to use the inbuilt functions to develop that so that you can classify huge data sets. Correct? So that's our motto now. So this code is actually you try to create 4 different data sets. To separate 4 different data sets, you need at least 2 straight lines. Okay, so our intention is that we want to see whether a multi-layer perceptron, single layer cannot do that because we know that single layer perceptrons are capable of handling linearly separable data only. But as soon as you enter into the problem of the XOR gate, this becomes a non-linear data set. So as soon as this is a non-linear data set, what you need at least 2 straight lines or some curves, right? So let us see how the perceptron, multi-layered perceptron, uh, decides to classify that. Okay, XOR problem, basically 4 classes. Fine. So out of the 4 data sets, 2 of them belongs to same class, other 2 belongs to other class, right? So class 0 and class 1. All right. So let's try to run this quickly. So I'll run and move ahead. So that was just to clear the workspace and right, the setup. Right now we move on to the data generation and visualization, because I have to create a data set, right? So this kind of data set creation we did already. So we create 4 different classes. Okay, yes. Again, in each of the class, we have the number of samples equal to 1000. So 1000 into 4, totally 4000. So since we are using the rand inbuilt function to create this, right, rand will create anything between 0 and 1, right, random numbers. So what we do in order to create 4 classes, we use a offset value, right, by adding and subtracting at various combinations, right. It is very clear that we can try to separate, right, we can separate the classes like this, right. So you can see that the first class, I do minus then plus of the offset. So second one is plus plus, then plus minus, then last minus minus. Yes. Okay, so like this, we try to create 4 different data sets, right? So then we visualize the data set, right? So this is how we visualize. We call a figure, plot the class A first row, all the columns, and second row, because first row is what I'm using it as my x coordinate, second row I'm going to use it as a y coordinate. So you can see here class A, all the 4 classes has all classes have 2 rows, and the right first row number of samples is 1000, 1 comma 1000, right, minus offset, and 1 comma 1000 plus offset. So y coordinate has every y coordinate has a plus 0.6 coming into picture. Okay, anyway, definitely we can change this and we can see what happens, right, how the classes will go away, right, they move far when you increase the offset, they come closer when you reduce the offset. If the offset is very less, maybe machine has some problem classifying them, right. You can do the trial and error and you can understand exactly what's going to happen with this value offset. Okay, fine. So we plot. Let's go to the plot part. Okay, so you can see that there are 4 classes created, right? So out of which we plotted similar the plots markers, right? 1 plus. So you can see that this class and this class have, though there are different data sets, right? But what we did, we try to plot them using the same markers like plus, because they belong to the same class in XOR community, in XOR gate, right? It's like 0 1 and 1 0, right? So minus 1 plus 1 will be the other two, which we try to plot using the stars, right? They're darker, correct? We didn't change the colors, we didn't apply any coloring over here. Okay, yes. All right, so this is what we did. in this phase. Then we define what are the inputs and what are the outputs. So this is just the data points we created over here. In the next section, we try to create what is our target for each of the class. Whenever a data comes from class A, we make sure that this belongs to -1. Class is -1. A and C -1, because you can see that A and C are something like this. One is minus plus and plus minus, right? We assign -1 to that. And later on, you can see the class B and class D, the target, the output of the machine is expected like this. So as +1, so this is plus plus or minus minus. So first quadrant and the third quadrant. Okay, so class A and class C belong to the second quadrant and the fourth. Okay, right. So like that, we actually assign the targets, because we have to give the targets so that machine learns, right? Then create the input, right? How many inputs you are going to give? You are going to give the inputs 4,000, right? Data points are passed. So first 1,000, then from class A, remain the second, starting from 1,001 to 2,000 is class B, 2,001 to 3,000 is class C, 3,000 to 4,000 is class D. Okay, so that's the input, and the target we are going to create in the same way, right? Again, I'm creating 4,000 target values, out of which the first 1,000 values are related to class A. What is related to class A? That is -1. You can say repeat the matrix. Class target, class A target, what is that? That's -1. -1 has to be repeated how many times? 1 comma length of class A. What is length of class A? Length of class A, you can see that. What is this length of this number? This is 1,000, correct? So totally 1,000 elements will be created. So that's for the first 1,000 samples. Then, so this is continuer. I'm saying the machine that I'm writing it in the next line, so it will neglect these 3 dots. Then rip mat, right? Once again, it's the length of class B. Then this, then this. So totally 1,000 plus 1,000 plus 1,000 plus 1,000. So 4,000. Sorry, my mistake. 4,000 samples are created corresponding to +1 or -1, which class the data set belongs to, in a variable called target. Okay, right. So let's run this, and we should be able to see the variables in the workspace over here after we run this section. So we can see here now. So let's look at the input vector. So you can see that this is the input vector. Yes, sir. Which is 2 rows, x comma y coordinates of all the 4,000 samples. Yes. Okay, at 1,000, 1,000 and 1,001, maybe there is some difference. You can see, right? This is lesser, this is higher, more. Now you see, this is more, this is less. So the class changed, right? Like that, definitely there will be change. I'll show the last difference between the last 2 classes as well, just to identify the change. You can see here, the second row is somewhat like this. First is high, low, this is high, this is negative, right? So something like that, you have a difference. Okay, right? So like that, we have the classes defined. Okay, that's about the input variable. Then also I have a target variable. You can see that the first 1,000 values are all -1 because it belongs to class A, right? After this, as soon as I move from 1,000 to 1,001, 1,001 belongs to class B, correct? So you can see that class B is all +1s. This will go up to 2,000. Immediately at 2,001 onwards, you have a change. You can see it's -1, -1. And at the end, 3,000 onwards, once again, +1 coming into picture, because that is class D. All right? Yes. So this is how the data set has been created and converted the data points into the required inputs and the targets or the outputs. Okay. Then after this, now we create the neural network and we train it. So here I try to show you to the creation of what is called as a feed forward network 5,3. Okay, and anyway, we had discussed in theory part that what do you mean by training ratio, validation ratio, testing ratio, right? Everything, right? We kept, now it is 1, indicating that this is 100%. Definitely you can set these values accordingly, right? Okay, then directly train the network. the neural network which is created by the name my ANN. I pass that, I give the inputs, and I pass the targets as well. Machine gets trained and results a learned neural network by the same name, right? And the various parameters out of which we are interested in the Y. Okay, fine. So let's do the training part now. Let's run this section. So machine will take some time to learn. Okay, so once the machine is completely trained, right, you can see the new parameters coming in into picture, like my ANN, because my ANN is the trained parameter, one of the trained parameters. Okay, fine. Then let's move further. So let's plot and see. Okay, so this is the targets and the network's response. Yes. Okay, and let me try to plot. One second, I'll run this part once again. Maybe it's not showing the proper classification. Just hold on. Run from beginning. Just a second. Yeah, now it's more clear. Correct. So we can see that the machine has learned the classification. Also, I simply added some colors so that it looks good. Okay, only that's the change here. So you can see that the blue colored graph, what we see here, is corresponding to one of the class. Okay, the blue area, and similarly the other color corresponds to the other area. So it actually has, you can consider that the non-linear classification, right, is possible, right, by the multi-layer perceptron. So the changes that you can make in this code just to verify what happens when you change the parameters could be something like this. One is this class offset. Okay, so keep changing, make it very less, bring the classes very closer, and check that whether machine learns. Okay, one thing is that, and the other thing is this, the network size. Okay, these are the two parameters which you can change, and you can make a table indicating that, okay, what's the offset, and how the machine will behave while classifying. Is it possible to classify, not possible to classify, right, etc. You can make a note to understand the changes. Similarly, you can make another table saying that what happens when you change the size of this. All right, so these are the various things that you can do, right, in order to understand what's going to happen, right, when you change the parameters. All right, so let's move further. So the next, okay, let me create a, let's create a new script. All right, so this is the fifth code, so I'll give a name similar, my code number 6. Okay, that opens up a new thing. So let's create a new section. So okay, so now our intention is okay, so previously we had two classes, XOR problem, right? There were two classes and we try to classify, right? Now there will be, will create a similar data set, but it will not be two class problem, it will be a four class problem. Okay, all the four classes we create will be different class. All right, let's see how a multi-layer perceptron is going to behave when we give a four class problem. Okay, so my code will be classification of four uh, classes by a multi-layer perceptron MLP. Okay, fine. So let's do this. Let's start with the similar codes we used to write earlier. First, let's set up by doing a clear close all. Then I'll do the CLC. Then I'll also warning of all. And let me see. So let's create another section after this. Now, the intention is to create four clusters of data. Okay, so that will be first. Let's define the number of samples. Okay, I think I can copy everything from my previous code, right? I'll directly copy just to save the time. All right. Okay, this still here. Everything I'll copy. And let's run this section. Okay, everything is clear now. So yeah, this is pretty much similar. The idea is that I wanted to create four classes. Four classes I already have created, but now let me try to plot. Now all the four samples are, or the four classes what we have created, they belong to different classes. All right, so I need to be careful while I plot. Okay, so I call figure, and let me plot. Okay, I'll copy everything from there. Plot is also very similar, but I'm going to change the markers. That's all. So that so this is what we are trying to plot now. So figure, I plot the class A data, one comma column, all the columns, class A, second row, all the columns. Let's say this. Okay, grid on, hold on, that's also fine for us. I'll just change the marker to say B for this. Okay, and maybe I'll change K X. So my marker is changed. Then star I'll change to D so that it becomes a diamond. Okay, so now let's see what happens. I'll save and I'll run. Yeah, so okay, colors I didn't change. Okay, oh okay, so this is blue diamond. Let me make a change. This is blue, sorry, blue diamond. Okay, now let me run this. Okay, you can see that the four classes have been created. All are with the various markers. Right, I can change this. Let me change one thing over here. I'll change this. This is say red X, and this is green diamond. Let's see. Let's check what's going to happen. Okay, just change of colors. Right, all the four different classes with four various colors. Okay, this is what is our data set. All right, so we created the data set, but anyway, we need to convert this into appropriate format. Okay, so that you can provide the inputs to the network. All right, so just to do that, I'll create four what you call four classes now. Yes. Right, so I'm trying to define my say the class a output, a required outputs for this. Okay, so I'll simply create like this, say a is equal to, now you see, since there are four classes, I'm trying to create the four various types of outputs now. So I'm expecting it's class A, -1, -1, -1, and +1. Okay, I'll add even the plus so that it looks familiar for me. So dash. Okay, this is for class A. Class B is equal to, you see the difference, right? It's -1, -1. Then I'll write +1, and okay, I missed the one over there in the previous line, sorry. Okay, you see here, right? And the next one will be -1 for me. Okay, then C is equal to, this is a class C, -1. Then we'll do the +1, -1, sorry, -1. I'll just take a transpose so that this becomes a vertical matrix. Okay, so column vector. That's my idea. C. Then D is equal to, this becomes +1, -1, -1, -1. Say transpose. Okay, so these are the four classes which we defined now. Okay, now let's try to define the inputs like we did earlier. So I'll try to call it as the input. Okay, so I think we call by this same name. Input is equal to, so bring the data set that is class A, class B, class C, and class D. Okay, class A space, class B space, class C space, class D. Okay, so this is the input we create now. Similarly, I have to define my targets, correct? So how did we define, or how we defined it earlier? Target is equal to, so use the very similar logic I'll show you here, right? So this is what we are going to do now. We created the input, now we are creating the output. Okay, okay, I think instead of naming them as class A target, B target, like that, we change it. I'll change it back. Okay, so I don't want to keep it simply A because you don't understand what it is, right? So this is class A target. So similarly, this is not B, this is class B target, right? Very similarly, this is class C target, and this is target. All right, so now I have to create this, right, the targets in a very similar fashion, right? So that will be okay, I think that will remain very similar, so I can copy, and then I'll check whether this is right. So the target is equal to ripmat. I just have to do the same idea. Let's just check. So I have to repeat the class A's target, which is this. Okay, one row, one times, row wise one time, columns, how many columns, that's equal to the length of class A. Length of class A is coming from here. Okay, fine, absolutely fine. So it remains same, so no change with this. Let's quickly run this and see whether it's running properly or not. Yeah. Okay, so this runs, and you can see that even let's look at the input and the target once, just to verify. So input is 2 rows, 4,000 columns as expected. Yes, we have that. Let's just verify. Yes, that's, and the target will be 4 rows, 4,000. You can see here right? First class is minus 1, minus 1, minus 1, 1, right? This has to change as soon as I cross 1000. You can say this is minus 1, minus 1, 1, minus 1. So 2000 onwards, something different. Minus 1, 1, minus 1. And the 3000 onwards, 1, minus 1, minus 1. Yes, this is what we expected. And yes, we are getting that. All right. Okay, so what we did so far, we created the data sets corresponding to 4 classes, converted that into the required format so that we can give them as input, and we can also provide the we can specify the machine that okay, this is what is my required output. All right. Okay, now the next part comes into picture wherein we design, train the neural network. Okay, I'll add the comment later. Fine. Okay, let's directly go to the network now. I'll define my network. Okay, this is my network. Now again, I'm going to use the same command, which is feed forward net. Okay, my ANN is equal to feed net. All right, and let's do one thing. We can use a similar one, or let me try to change and see what happens. Okay, 4 and 3. Let's try to define like this. Okay, feed forward network. This is what is my A. Okay, this is my ANN. I create this. Now, I have to define the parameters for training, validation, and testing, right? So this is my ANN dot. How to it's a parameter, so I think I have to write a divide parameter. So divide parameter dot, this is train ratio. I want to keep everything for training, so I don't want to make others, or others I can directly copy from there. Okay, so okay, so the training part is done here. Specification of the training, right? I added up here. Okay, now my next idea is that I have to do the training. Okay, so perform the training you by specifying what is output that you are expecting. So this is my ANN is what I'm expecting as an output, one of the output. Then you get a trained matrix, so that's TR. If you are not worried about, you can even put you're not worried about what you get here, right? You can specify like that if you are not using it. Okay, then I get the output and I get an error, right? So this is the result of a train. What you are training of my neural networks, comma, I'm training what you're passing. I think you are going to pass your input, right? So also uh, you will pass what are the targets. So that performs the training. Okay, so anyway, let's check whether what we have written now is correct. Will there be any error? Okay, I think there is something input. Yeah, sorry. Let me run this section again. Oh, sorry, INTUT. Sorry about that. INPUT. INPUT control. So you can see that the my ANN has been created here, indicating that yes, you have successfully we run the section successfully. Okay, now I just have to test my neural network. So what I do, I add another section to this. Okay, so and this is a testing part. let's write some code related to this.
Yes.
Right. So let's try to decode the neural network's response first. Okay. Uh, Fine. Let's try to write something like this. I get two parameters, m comma I. They are directly coming from my target values. Okay. So the maximum value present in the target values. Okay, so target max of target, fine, and I should get another one, that is once again it is m comma j, because m will remain same because the size is same. All right, and this is minimum again coming from target. Okay, right, we are trying to read the parameters, right? So one from the target and okay, I'll do one more thing. Let me check this. Max from, not from the target, from the predicted class I need. So the predicted class is actually this y, right? So I'll do a change here. This is y. Okay, let's do this. Let's see. Instead of that method, this is going to work fine now. Okay. Now, anyway, this m is not required, so I can actually neglect this, right? Because the same m comes in this. That's why if you write another m here, it keeps on highlighting that with the red color, saying that this is not being used as you are reading m once again at a different stage. So don't read anything here. That makes lesser operations for a machine, right? Program runs faster. Okay, that's the reason why I am neglecting that. Okay, right. Now, let's define the length here. N is equal to length of my response. So that is Y, right? That's the length of your sequences, number of all samples. Then let's try to hold a variable. Let me put it as k. I'll initialize 0 because this is the one which I'm going to use to hold the count of misclassified samples, right? The data belongs to class 1 or class A, but machine classified that as a class B. So that's an error. So how many such errors will happen out of your 4,000 samples? I'm going to hold that in this K. Okay? Yeah. Right. So let's try to check that whether there is any misclassified sample. So how do you check that? I'll go use a if condition. So if, right, we know that there is a find function of I minus j, right? If there is so if you remember, find, that's fine, otherwise just look at this. This is going to give you the complete details of the help, right? So returns a linear index corresponding to the non-zero entries of array. So you perform I minus j, right? I is an array you already got from the targets. J you are getting from the actual values, right? Which is returned from the which is written by the machine returned, okay, this sample belongs to this class, this sample belongs to this class. So this I minus j, if both are same, in the sense I is the actual truth, ground truth, j is the machine's classification. If they are same, when you subtract you should get a 0, right? So you see here, it returns linear indices corresponding to non-zero entries. Non-zero, number of non-zero entries in I minus j means what? That is a misclassification.
Yes.
Right? Are you okay? So find if there are any non-zero entries in I minus j, those points are corresponding to the misclassification. Right? What is my intention? My intention is to catch them in a variable, right? I simply want to catch it in a variable k. What do you do? So simply do this. This is, if this is the case, increment k. So, right, what do you do? K equal to, I don't have to put a loop here, right? No need of going for a for loop or something. Like if I'm writing a C code or something, I definitely need a for loop here. How many number of I minus j I need to first find out, then you increment k, right? So that is not needed here. Directly you can do that in MATLAB. Simply calculate the length. Length indicates how many samples are there, where it is find. Inside this find of I minus j, even you can do j minus I, doesn't matter. Okay, find I minus j is a vector. In that vector, right, how many non-zero entries are there, you can calculate the length of that. Okay, so length of find of I minus j is what I want. I'll put a semicolon. I don't want to show this as output. So as a this thing, I have to end this loop. So end. Okay, so that gives how many number of samples are misclassified. Okay, so let's convert this into okay, let's convert this into the accuracy, right? So okay, I need to print something, so I have to use a f printf, right? Inside the single quote you can enter the text. So accuracy of the model is equal to okay, let me specify percentage dot that's 0.1. I just want a one decimal place. Okay, 0.1 f percentage maybe I can write samples. So that's the accuracy, and I just want to add a backslash n to go to the new line, and I will specify what I want to print over there. It's 100 into 100 into k is the error. So if you want to accuracy, it's n minus k. Sorry. So I just have to write the capital N minus k, because n has been calculated just now. You can see it's a length of y, right? So that minus the misclassified samples, right? So simply you can write that. Sorry, I want a percentage, my mistake, divided by the total number of samples. I cannot miss this. Okay, so write this and the close. So that will print the percentage of accuracy. Okay, let's try what's going to happen here. Let's run this section. So this says accuracy is 100%. All the, you can see here the result.
Yes, sir.
So
Yes, sir.
this actually classified the all the machine learned everything properly. It could be the one possible reason is the data set is less, just 4,000. It's huge for human calculation. It is huge, but 4,000 is very negligible amount of data for a machine, right? So also the classes are very well defined, right? There is a actual properly there is a bias, right? You have offset or bias between the classes, which is properly defined. So maybe because of that, also that reason as well, the machine is able to capture the difference among the four classes, right?
Yes.
Properly. Okay, so that's how we can design a multi-layer perceptron to classify the four classes. Okay, so in the next class, I'm going to show you even the visualization, like we did for the previous programs, wherein
Yes.
I want to see what machine has derived. Is it a straight line? Is it two straight lines, or is it non-linear curve, one single curve,
Yes.
two curves to differentiate among these classes? I want to visualize that as well. So we add some more code below this to do that. That will be our first objective in the next class.